Okay, hello. So we have another activity planned for today, right? So today we'll try to delve a little bit more into what happens to a structure during, resonance. Okay. So if you recall, during resonance, the frequency of the base motion matches with the natural frequency of the structure, right? And now suppose the structure is undergoing resonance. The amplitude of the structure during resonance is governed by another parameter, okay, and that parameter is referred to as damping ratio, okay. And so what is damping ratio? So maybe it's much easier if I demonstrate it through a small activity, right? So consider this structure which is on your right. Suppose I displace it by a small amount and I leave it, right? And consider the same phenomena here. I have deflected it by a small amount and now I am leaving it, right? So clearly this structure was undergoing oscillations for a longer time before it came to rest, whereas in fact this structure hardly underwent more than 1 or 2 cycles before it came to a complete halt, right? And so we can say that the structure on your left, it has less damping in comparison to the structure on the right, right? And so this damping ratio is a dimensionless quantity which is reflective of that after how many cycles, let us say the initial amplitude, say it is, let us say u naught, it maybe gets reduced to let us say 0.2 u naught, right? So and we are going to idealize the damping for this activity. So there is a form of damping referred to as viscous damping, right? And if we assume that, then it can be shown that the damping ratio is inversely proportional to the number of cycles taken for the structure for its amplitude to be reduced by a given factor, right? So for instance, if let us say the number of cycles taken for this structure are maybe around 2, and for this structure the number of cycles taken are around maybe, so you can think it underwent many more oscillations, right? Maybe around 10 to 15, right? So let's stick with 10. Okay, so if it took 10 cycles for this structure for its response to be reduced by let us say 90%, and it took only just 2 cycles for this structure for its response to be reduced by 90%, then the damping ratio of this structure is 5 times smaller than the damping ratio of this structure, right? So now why this parameter damping ratio is important, right? So now maybe we can have a little bit look at relation, right, of the amplitude of deformation, right? So it is governed by all these terms which are appearing on the right hand side, right? And so this amplitude of deformation is nothing but the amplitude of the motion at the top with respect to base, okay? So now what is it going to be a function of? It is going to be a function of how much was the amplitude of acceleration at the base, right? So in the previous activity when we were moving the base, right? So clearly the base will have some acceleration, right? And how much amplitude we get at the top, that is directly proportional to what is the acceleration of the system at the base, right? And it is inversely proportional to the square of the natural frequency, right? And so this is effectively giving us really what is the static value of the displacement if the acceleration were applied statically, right? Now multiplied with this term is this quantity called as the deformation response factor, okay? And so this factor is dependent on 2 parameters, okay? So one is the ratio of the oscillation frequency and the natural frequency of the structure, and there is another parameter which is what I just mentioned, which is the damping ratio, right? So this xi variable indicates the damping ratio, right? And so if you look at this curve, so let us say let us consider this curve for a damping ratio of 2%, right? So we typically depict damping ratios in terms of percentages, right? So you can see that this deformation response factor, it's going to increase as we increase the forcing frequency omega, and when we are very close to the natural frequency, that is when this ratio becomes 1, this deformation response factor becomes very large, right? So you can clearly see that for 2% damping it can reach up till a value of 20, right? And then once we exceed the forcing frequency beyond the natural frequency, it again starts becoming smaller, right? And that is what we demonstrated in the previous activity, right? That as we started, with slow deformations, the amplitude was not much, and then when we reached the resonant frequency, then the amplitude became very large, right? So this curve is indicating, in a sense, whatever observations we were able to manifold in the previous activity, right? And now I want you to focus on the blue and the I want you to compare the blue curve with the red curve, right? And how is red curve differing? The red curve corresponds to a much higher value of damping ratio, right? So in this case the damping ratio is 15%, so which is around 7.5 times greater than the damping ratio corresponding to the blue curve, right? And so we can see that when at resonance, that is when omega by omega n is equal to 1, there is a sudden difference in this deformation response factor, right? It reduces from a value of more than 20 to a value, so like the y-axis is on the logarithmic scale, so this value is around maybe 3, right? So there is a 7 times difference in the value of the deformation response factor, and it is actually true that at the resonance, this is in inverse proportion to the damping ratio, because your damping ratio is differing by a factor of around 7. That is the factor by which even your deformation response is varying, right? So now what I want to demonstrate in this activity is that if let us say you have two structures, right, and let us say both of them are subjected to the same base motion, right, and so that will take care of the fact that the value of A naught is going to be same, right, and also suppose we are able to ensure that the natural frequency of both these structures are same, right, so that is going to ensure that omega n is also same, right, and so under this condition whatever difference we obtain in the response of the two structures, that will be solely due to the effect of damping, right, and so that is what I and my student Nitish, we try to achieve, okay, and it was a difficult exercise for us because when we started playing with the stiffness and the mass properties, it was not easy for us to have two systems whose natural frequency was same and yet the damping ratio was distinctly different, right? And so this system, which has a higher damping ratio, I have already explained, it is made up of these erasers, right? And on the other hand, to construct a system which had a much lesser damping ratio, so we resorted to using these spaghetti sticks, right? So they may not appear as distinct strands, but this whole member is made up of I think around 7 or 8 spaghetti sticks, right, which are glued together using epoxy, right, and at the top we still have that eraser, right, and so I have worked with spaghetti sticks before, and so I know that they have much more elasticity and they have less damping ratio, right, and so now what we'll try to do is we'll again subject the these two structures to an oscillatory base motion, and we'll try to make this particular structure, the one to your left, we'll try to make it undergo resonance, okay, and so what I want you to see is that when it is undergoing resonance, you compare the amplitude of this structure with this structure's amplitude, right? If everything is as per the formulation just shown, then this structure's amplitude should be much higher than this structure's amplitude, right? So let us see if it actually happens, okay? So I am starting with low frequencies, and now I am gradually increasing the frequency, and now I am reaching a frequency at which the structure to your left has started resonating, right? And I hope it is evident if you compare the response of the structure to your left and to your right, that it is the structure on the left which has a very high amplitude in comparison to the structure on the right, okay? And this is precisely what happens if you have, let us say, a difference in the damping ratio, because the structure to your left had significantly smaller damping ratio than the structure to your right, its amplitude during resonance was much higher than the amplitude of the structure to your right. Okay, so thank you for watching.